There is a number so small that the human mind struggles to hold it, not because it is merely large or merely complicated, but because it seems to belong to a category beyond ordinary comparison. A number so extreme that every familiar reference point collapses beneath it. Not one in a million, not one in a trillion, not one in all the grains of sand scattered across every beach on Earth. A number so remote from everyday experience that language itself begins to fail. Imagine for a moment that you are standing alone beneath a perfectly dark sky. No city lights, no passing aircraft, no distant glow on the horizon. Only the vast dome of the night stretching above you, filled with stars whose light began its journey long before human civilization existed. As you look upward, it becomes clear that the universe is not merely large. It is old, ancient beyond intuition. Every star becomes a reminder that reality has a history extending billions of years into the past. Now imagine tracing that history backward, past the formation of Earth, past the birth of the sun, past the first stars, past the first galaxies, past every atom that now exists in your body. Continue moving backward through time until the universe itself begins to shrink. Galaxies draw closer together, distances contract, temperatures rise, the cosmos becomes denser, hotter, more compressed. Continue further still until all familiar structures disappear. No planets, no stars, no light, no atoms, no space as we ordinarily understand it. Only the unimaginably strange conditions of the earliest universe. It was while thinking about those conditions that the mathematical physicist Roger Penrose arrived at one of the most astonishing calculations in modern science. He was attempting to estimate how special the early universe must have been in order for the cosmos we observe today to exist at all. His answer was not merely surprising, it was disturbing. The number he produced was approximately 1 chance in 10, raised to the power of 10 raised to the power of 123. Even stating the figure feels absurd. There are not enough particles in the observable universe to write it out in full. There are not enough pages, not enough stars, not enough time. And yet Penrose was not describing something imaginary. He was describing the apparent improbability of the universe beginning in precisely the low-entropy state required for galaxies, stars, planets, chemistry, biology, and eventually conscious observers to emerge. Whether one agrees with every detail of the calculation is less important than the question it forces us to confront. Why was the beginning so special? As the night deepens around us, this question becomes strangely personal, because the story of the universe is also your story. Every atom in your body was forged in ancient stars. Every breath you take is connected to processes that began billions of years ago. The calcium in your bones, the iron in your blood, the oxygen filling your lungs all emerged from cosmic events that occurred long before the first human being ever looked up at the sky. You are not separate from the universe. You are one of the ways the universe became aware of itself. And yet awareness introduces a puzzle that has haunted physics for nearly a century. To understand it, we must leave the realm of stars and galaxies for a moment and descend into a much stranger domain, the quantum world, the world beneath matter, the world beneath certainty, the world where reality itself appears reluctant to choose a single form. Early 20th century physicists discovered something deeply unsettling about nature. The smallest components of reality did not behave like tiny billiard balls moving through space along definite paths. Instead, they behaved like possibilities. An electron could exist in multiple potential states. A photon could appear to travel through multiple paths. The future seemed not fully determined, but spread out into a cloud of probabilities. To describe this strange behavior, physicists developed one of the most successful mathematical frameworks ever created, quantum mechanics. The equations worked with extraordinary precision. They predicted experimental results to astonishing accuracy. Yet hidden inside the theory was a mystery that remains unresolved even today. According to the standard mathematical description, a quantum system evolves smoothly as a wave function. This wave Function does not describe one definite outcome. Instead, it describes many possible outcomes simultaneously. The equations governing this evolution are elegant, predictable, deterministic, and yet whenever an observation is made, only one outcome appears, one result, one fact, one reality. Somewhere between possibility and experience, something changes. The wave of possibilities becomes a single event. The question is simple enough to ask: what causes that change? For generations, physicists have debated the answer. Some argue that observation itself plays a role. Others argue that observation is merely an illusion, hiding deeper processes. Still others suggest that every possibility actually occurs in parallel realities beyond our perception. Each interpretation attempts to explain the same strange transition. How does uncertainty become certainty? How does possibility become fact? How does a universe of probabilities become the world you experience right now? As we continue our journey, these questions will lead us into some of the most profound territory in science and philosophy. They will carry us through thought experiments involving cats that are simultaneously alive and dead, through photons that appear to make decisions after they have already completed their journeys, through observers who disagree about what reality itself contains. And eventually, they will bring us back to the beginning, back to the earliest moment of the cosmos, back to the first fraction of the first second, because there is an unsettling possibility hidden inside the foundations of quantum theory. If physical reality requires observation to become definite, what happened before observers existed? When the first stars had not yet formed? When the first atoms had not yet appeared? When there were no planets, no life, no minds, no eyes looking out across space? What transformed the primordial possibilities of the universe into the definite cosmos that would eventually give rise to us? For now, do not rush toward an answer. Allow the question to remain suspended, like a distant star reflected on still water, because sometimes the deepest mysteries reveal themselves only when we stop trying to solve them immediately. And as the universe slowly expands around us once more, carrying galaxies apart across unimaginable distances, we begin to approach the strange territory where quantum mechanics and cosmology meet. A territory explored by one of the most imaginative physicists of the 20th century. A man who believed the universe might be far more participatory than anyone had suspected. And that is where our journey continues. For now, settle deeper into the darkness. Listen to the silence between the stars. And when you're ready to continue exploring the deepest mysteries of existence, join us again here on Space Sleep Theory, where the universe becomes a little stranger, a little larger, and a little more beautiful each night. There is a peculiar habit of the human mind. Whenever we encounter something strange, we instinctively try to translate it into something familiar. We imagine atoms as tiny solar systems. We picture light as streams of particles. We describe space as a kind of invisible container in which objects move. These mental shortcuts are useful because they allow us to navigate a reality that is far too vast and complicated to hold in full. Yet, there comes a point where familiarity becomes a trap. The quantum world is one of those places. It is a domain where every analogy eventually breaks down, where the deepest layers of nature refuse to behave according to the expectations built from everyday experience. And it is here, in this strange territory beneath matter itself, that one of the most profound questions ever asked begins to emerge. Not what the universe is made of, not how old it is, not even why it exists, but something more unsettling. What exactly is reality before it is observed? For most of human history, the answer would have seemed obvious. A mountain exists whether anyone looks at it or not. The moon circles Earth, whether anyone watches the sky. A tree falling in an empty forest still falls. Reality appears independent of observers. It seems to possess definite properties, regardless of whether a conscious being is present to witness them. This assumption is so natural that it rarely receives attention. It forms the invisible background against which all ordinary thinking takes place. Yet, the development of quantum mechanics in the 20th century forced physicists to confront the possibility that reality at its deepest level may not be structured in the way common sense suggests. The equations describing microscopic systems do not tell stories about definite objects moving through definite trajectories. Instead, they describe clouds of possibility, distributions of potential outcomes that evolve smoothly through time until something extraordinary occurs. To understand why this became such a problem, imagine a single photon moving through space. In classical thinking, the photon must occupy one location at a time. It follows one path. It possesses one history. But quantum mechanics describes the situation differently. Before measurement, the photon is represented by a wave function, a mathematical object containing information about every possible outcome. The wave function does not say the photon secretly chose one route that we simply have not discovered yet. It describes a state in which multiple possibilities coexist. This is not merely ignorance. It is not a lack of information waiting to be filled in later. The mathematics itself behaves as though the possibilities are physically relevant. They interfere with one another. They influence outcomes. They leave signatures in experiments that can be measured and repeated. The most famous demonstration is the double-slit experiment, a deceptively simple arrangement that has unsettled generations of physicists. Imagine a barrier containing two narrow openings and a screen placed behind it. Particles are fired one at a time toward the barrier. If the particles behave like tiny objects traveling through definite paths, each one should pass through either the left slit or the right slit. The resulting pattern on the screen should consist of two bands corresponding to the two openings. Yet when no measurement is made to determine which slit each particle passes through, an entirely different pattern appears. A delicate series of interference fringes gradually emerges. The pattern resembles the behavior of waves overlapping and interacting with one another. Somehow, each particle behaves as though it explored both possibilities simultaneously. Even more remarkably, the interference pattern builds up one particle at a time, as though every individual particle is interfering with itself. For decades, physicists have repeated this experiment with photons, electrons, neutrons, atoms, and even complex molecules containing dozens of atoms. The result remains the same. The universe appears unwilling to reveal a single, definite path until information about that path becomes available. The moment a detector is installed to determine which slit the particle travels through, the interference pattern disappears. The wave-like behavior vanishes. The particle suddenly behaves as though it had chosen a definite route all along. Nothing else changes. The geometry remains the same. The apparatus remains the same. Only the availability of information changes. And with that change, reality itself appears to reorganize. As the implications began to sink in, physicists found themselves confronting an uncomfortable possibility. Perhaps the world we experience is not built from definite facts at the deepest level. Perhaps definiteness emerges only under particular conditions. The equations seem to suggest that possibility is more fundamental than actuality. Potentiality comes first. Certainty arrives later. Yet this immediately raises another question. What exactly qualifies as an observation? Does reality require a conscious mind? Does a detector count? Does a photographic plate count? Does a grain of dust count? The history of quantum mechanics became, in many ways, the history of physicists attempting to answer this single question. Niels Bohr, Werner Heisenberg, and the architects of what became known as the Copenhagen interpretation approached the problem with a practical mindset. The theory worked. Its predictions matched experiments. Rather than worrying excessively about what the wave function represented, they focused on the fact that measurements produced definite outcomes. Somewhere between the microscopic world of possibilities and the macroscopic world of experience, a transition occurred. The details remained mysterious, but the success of the theory encouraged many physicists to accept the mystery as a fundamental feature of nature. For decades, this approach dominated scientific thinking. Students learned how to apply the equations. Engineers built technologies based upon them. Yet beneath the extraordinary success lingered an unresolved conceptual gap. The equations governing the evolution of the wave function never actually described the moment when possibilities became facts. Imagine reading a novel in which every event unfolds with perfect logic until the final chapter, where the most important transformation occurs off the page. The characters arrive at a crucial doorway. The next page simply announces that everything has changed. No explanation is given. No mechanism is described. Readers are told to accept the transition because the story works. This is how many critics have viewed the measurement problem. Quantum mechanics provides exquisite mathematical descriptions of evolving possibilities. Yet the transition to observed reality remains strangely absent from the equations themselves. The mystery deepens when time enters the picture. Most people imagine cause and effect flowing in a straightforward sequence. First, an event occurs. Then, its consequences follow. Yet certain quantum experiments seem to blur this distinction. Among the most famous are the delayed choice experiments proposed by the physicist John Wheeler. Wheeler asked a question so strange that it almost sounds like science fiction. What happens if the decision about how to measure a particle is made after the particle has already entered the experiment? Intuition suggests the particle must have already decided what it was doing. Surely the past is fixed. Surely a photon cannot wait for a future measurement before determining how it behaved. Yet experiment after experiment suggests something subtler. The behavior recorded depends on the final measurement arrangement, even when that arrangement is chosen after the particle has already passed critical points in its journey. The mathematics remains perfectly consistent. No information travels backward through time. No paradox emerges. And yet the familiar picture of particles following definite histories begins to dissolve. Wheeler became fascinated by the implications. The universe seemed less like a machine unfolding independently of observers, and more like a participatory process in which observation and reality were woven together in ways not yet fully understood. As Wheeler reflected on these ideas throughout the later decades of his life, he found himself drawn toward an increasingly radical possibility. What if observers are not merely passive spectators looking at a finished universe? What if observation participates in the formation of reality itself? Not in the simplistic sense that thoughts create matter, but in the deeper quantum sense that facts emerge through acts of registration. The idea remained controversial. Many physicists rejected it. Others found it impossible to ignore. Wheeler himself was careful not to claim certainty. He understood that the measurement problem remained unresolved, yet he could not escape the feeling that the universe was trying to tell us something profound through these experiments. Tonight, as we drift farther into this mystery, notice how different the question has become from the one we began with. We started by wondering about the astonishing improbability of the universe's initial state. We now find ourselves examining the nature of reality itself. And slowly, almost imperceptibly, the two questions are beginning to move toward one another. Because if observation plays a fundamental role in transforming possibilities into facts, then the early universe presents a challenge unlike any other. Long before galaxies formed, long before planets emerged, long before the first living cell appeared, the cosmos existed in a state vastly different from the world we know today. Yet somehow, the universe arrived at the definite reality from which everything else followed. The path from possibility to actuality was taken. The question waiting for us in the darkness ahead is simple to state and difficult to answer. If observers appear late in cosmic history, what was participating in reality before observers existed? As we continue our journey, that question will lead us directly into Wheeler's most famous idea, an idea that attempts to connect quantum observation, cosmic history, and the existence of the universe itself into a single astonishing vision. Imagine that you are standing at the edge of the observable universe, not physically, because no such location exists, but mentally. Imagine looking outward in every direction at once. Billions of galaxies drift through the darkness. Rivers of stars spiral through immense gravitational structures. Ancient light, traveling for nearly 14 billion years, continues its silent journey across expanding space. Everything appears complete, finished, self-contained. The cosmos seems like a vast stage upon which events unfold according to impersonal laws, indifferent to whether anyone is present to witness them. This image is deeply comforting because it places humanity in a familiar role. We are spectators. The universe is the performance. Reality exists independently, and we merely discover what is already there. Yet John Archibald Wheeler spent much of his life wondering whether this picture, elegant as it appears, might be fundamentally incomplete. Wheeler was not a fringe thinker operating at the margins of science. He stood near the very center of 20th century physics. He worked with some of the greatest scientific minds who ever lived. He studied under Niels Bohr, collaborated with Albert Einstein, supervised Richard Feynman, contributed to nuclear physics, helped shape our understanding of gravitation, and introduced terms that have become inseparable from modern science. The phrases black hole, wormhole, and quantum foam all emerged from Wheeler's imagination. He possessed an unusual gift for seeing beyond the technical details of equations and asking what they implied about reality itself. While many physicists focused on solving specific problems, Wheeler repeatedly returned to deeper questions. What is information? What is observation? Why does the universe appear comprehensible? Why should mathematics describe reality so effectively? And perhaps most importantly, what role do observers play in the existence of the world they observe? As he grew older, these questions became increasingly central to his thinking. The strange lessons of quantum mechanics had never fully settled into a comfortable framework. The equations worked beautifully, but the conceptual foundations remained unsettled. Wheeler noticed something that many physicists preferred not to emphasize. Quantum theory consistently describes systems in terms of possibilities until an observation occurs. The act of observation is not a minor detail tucked away at the edge of the theory. It appears directly at the point where possibilities become actual events. The universe, at least in its mathematical description, seems to care about the existence of records. It seems to distinguish between what could happen and what has happened. This observation led Wheeler toward one of the most provocative ideas in modern physics. He began to suspect that observers might not simply inhabit the universe. They might participate in bringing aspects of reality into definite existence. The phrase he eventually used was simple and memorable: the participatory universe. At first glance, the idea sounds mystical, but Wheeler intended it as a serious attempt to confront the implications of quantum theory. If observation plays a fundamental role in transforming possibilities into facts, then observers cannot be treated as entirely separate from the reality they observe. The observer becomes part of the story, not an external witness standing outside the system, but an active participant woven into the structure of reality itself. To understand why Wheeler found this idea compelling, imagine a book whose final chapter somehow influences the meaning of every chapter that came before it. As you read the story, earlier events appear ambiguous. Multiple interpretations remain possible. Then, upon reaching the conclusion, the entire narrative suddenly crystallizes into a coherent whole. The ending does not travel backward through time and rewrite previous pages. Yet, it determines how those pages are understood. Wheeler suspected that quantum reality might operate in a surprisingly similar fashion. Observations made in the present appear to help define aspects of the past. Not by altering history, but by determining which of several possible histories becomes physically meaningful. This intuition found its most dramatic expression in the delayed choice experiments. Wheeler loved these experiments because they forced people to confront assumptions they rarely noticed themselves making. Consider a photon emitted from a distant source. The photon enters an apparatus where it may follow two possible routes. If the experimental setup is arranged one way, the photon behaves as though it traveled both paths simultaneously, producing interference. If the setup is arranged differently, the photon behaves as though it traveled only one path. The remarkable feature is that the choice of measurement can be delayed until after the photon has already entered the apparatus. Classical intuition insists that the photon must have already decided what it was doing. Yet the experimental outcome suggests that reality resists such straightforward descriptions. Wheeler often dramatized the implications by expanding the scale of the thought experiment from laboratories to the cosmos itself. Imagine a photon emitted by a distant quasar billions of years ago. During its journey toward Earth, the gravitational field of an intervening galaxy bends its path. In a sense, the photon may travel around one side of the galaxy or the other. Modern instruments allow astronomers to examine arriving light in ways that reveal either path information or interference effects. Wheeler's provocative question was this: if the final measurement determines which description applies, what sense does it make to say the photon had a definite history before the measurement occurred? The photon has been traveling for billions of years, yet the experiment seems to imply that the reality assigned to that journey depends on observational choices made in the present. Many physicists interpret these experiments cautiously. They emphasize that quantum mechanics predicts probabilities, not retroactive causation. No message travels backward through time. The equations remain internally consistent. Yet Wheeler believed something important was being revealed. The universe does not seem to contain fully formed facts waiting patiently to be uncovered. Instead, reality appears relational. Facts emerge through interactions. Observations matter. Information matters. Records matter. The cosmos is not simply a giant machine grinding forward independent of all observers. At some level, observation appears woven into the very fabric of existence. As these ideas developed, Wheeler introduced another phrase that would become one of his most famous contributions: it from bit. The phrase was short, almost playful, but its implications were enormous. By it, Wheeler meant physical reality itself. Every particle, every field, every star, every galaxy, every measurable thing. By bit, he meant information, the answer to a yes or no question. Wheeler's suggestion was that information is not merely something stored within physical systems. Information may be more fundamental than the systems themselves. The physical world could emerge from acts of information acquisition and registration. Pause for a moment and consider how radical this proposal truly is. For centuries, science largely assumed that matter comes first. Objects exist. Information is simply something we learn about those objects. Wheeler inverted the relationship. Perhaps information comes first. Perhaps the physical world emerges from a deeper informational foundation. The idea remains speculative, but it continues to influence fields ranging from quantum information theory to modern approaches to gravity and cosmology. Even physicists who reject Wheeler's broader philosophical conclusions often acknowledge the remarkable importance of information in contemporary physics. The deeper Wheeler followed this line of thought, the more he found himself confronting a puzzle that stretched all the way back to the beginning of the universe. If observation participates in the formation of reality, what happens when we consider the earliest moments of cosmic history? Before stars existed, before planets formed, before life emerged, before any observer resembling ourselves appeared anywhere in the cosmos. Quantum cosmology describes the early universe using wave functions and probability distributions. Yet wave functions represent possibilities. Somehow those possibilities gave rise to a definite cosmos. The galaxies around us exist. The stars exist. The atoms in your body exist. The universe is not merely potential. It is actual. Wheeler's answer was not a complete solution, but a provocative suggestion. Perhaps observers in the universe exist in a kind of self-consistent relationship. The cosmos gives rise to observers through billions of years of cosmic evolution. Observers, through acts of measurement and participation, contribute to the emergence of a definite reality. The picture resembles a great cosmic circle rather than a simple chain of cause and effect. Reality gives rise to observers. Observers participate in reality. The beginning and the end become connected in ways that challenge ordinary intuitions about time and causation. Whether Wheeler was correct remains a matter of debate. His participatory universe has never become a universally accepted interpretation of quantum mechanics. Many physicists prefer alternative explanations. Some embrace many worlds. Others favor hidden variable theories. Still others seek entirely new frameworks that might dissolve the measurement problem altogether. Yet Wheeler's questions refuse to disappear. They linger because they point towards something genuinely unresolved at the heart of modern physics. We possess extraordinarily successful equations. We can predict experimental outcomes with astonishing precision. We can build technologies that depend upon quantum phenomena. Yet we still do not fully understand what observation is or why the universe seems to care about it. And so, as the stars continue their silent motion across the night sky, we find ourselves approaching an even deeper mystery. Wheeler's participatory universe raises a question that cannot be avoided forever. If observation plays a role in making reality definite, and if the early universe existed long before familiar observers appeared, then what exactly was happening during those first moments after the Big Bang? Was the cosmos waiting? Was it evolving as a vast cloud of possibilities? Or does the answer require us to rethink what we mean by observation itself? To explore those questions, we must leave Wheeler for a moment and turn toward the extraordinary experiments that pushed quantum mechanics into its most bewildering territory. Experiments involving erased histories, contradictory observers, and realities that seem to depend upon who is asking the question. It is there, in the strange borderland between information and existence, that the mystery deepens further. The most powerful rhetorical move in the entire presentation is also the least obvious. It is not the appeal to cosmology. It is not the appeal to fine-tuning. It is not even the appeal to the Kalam argument. The decisive move occurs much earlier, when the audience is persuaded that quantum mechanics somehow places consciousness back into the foundations of reality. Everything that follows depends upon that step. If consciousness truly occupies a privileged position in the operation of the universe, then the search for a cosmic observer becomes almost unavoidable. If observation is necessary for reality to become definite, then one naturally begins asking who performed the first observation. If physical reality requires awareness in order to become actual, then awareness appears more fundamental than matter. Once that conclusion is accepted, the distance between physics and theology suddenly appears much shorter than it did before. The difficulty is that modern quantum theory does not clearly establish any of this. To understand why, it is worth remembering what the measurement problem actually is. The measurement problem is not the problem of consciousness. The measurement problem is the problem of obtaining definite outcomes from quantum evolution. That distinction matters. A quantum system can exist in a superposition of possible states. The Schrödinger equation describes how those possibilities evolve through time. Yet when measurements are performed, experimenters observe definite results. A detector clicks. A screen records a position. A laboratory notebook receives a number. The question is not why a conscious mind experiences the result. The question is why a result exists at all. These are different questions. For much of the 20th century, they were frequently blurred together. Some physicists, philosophers, and popular writers suggested that conscious observation itself might be responsible for collapse. The idea possessed obvious appeal. It seemed to place human awareness at the center of reality. It appeared to explain why definite outcomes emerge from indefinite possibilities. Unfortunately, appeal is not evidence. When one examines the actual development of quantum foundations over the last 50 years, a different picture emerges. The key concept is decoherence. Imagine a quantum particle existing in a delicate superposition. If that particle could remain perfectly isolated from everything else, its quantum behavior would persist. In practice, however, complete isolation is almost impossible. Every interaction with the environment, every photon, every air molecule, every thermal vibration creates entanglement between the system and its surroundings. The environment, effectively, records information about the system. The result is that interference effects become inaccessible. The quantum state does not literally disappear, but from the perspective of observers embedded within the environment, the system behaves as though it has chosen a definite outcome. Decoherence does not solve every interpretive question. Even its strongest advocates acknowledge this. What it does accomplish is something significant. It removes consciousness from the center of the process. A Geiger counter does not require a mind in order to register radiation. A photographic plate does not require awareness in order to record a track. A cloud chamber does not wait for a philosopher before forming visible droplets. Physical systems interact with physical systems continuously. The universe was producing records long before human beings appeared. Stars were forming. Galaxies were colliding. Atoms were binding into molecules. Supernovae were exploding. None of these events appears to have required conscious supervision. This does not prove that consciousness plays no fundamental role, but it does mean that the strongest versions of observer-dependent quantum mysticism no longer enjoy the privileged position they once held. The delayed choice experiments discussed in the presentation provide an instructive example. These experiments are among the most astonishing achievements in modern physics. They demonstrate that quantum systems do not fit comfortably into classical categories such as particle and wave. They reveal deep features of quantum correlations that continue to challenge intuition. What they do not demonstrate is retrocausation, nor do they demonstrate that human decisions reach backward through time to determine past events. The mathematics of quantum mechanics predicts the results perfectly without requiring either conclusion. The mystery lies in our classical expectations, not in any demonstrated violation of causality. The same observation applies to the quantum eraser experiments that frequently appear in popular discussions. Descriptions of these experiments often suggest that reality itself is being rewritten after the fact. The actual situation is more subtle. The interference pattern emerges or disappears, depending upon how information is correlated within the overall experimental arrangement. No message travels into the past. No observer edits history. No conscious act reaches backward through time. The experiments are extraordinary enough without adding claims they do not support. Wigner's friend occupies a similar position. The thought experiment is fascinating precisely because it exposes tensions between different ways of describing measurements. Yet, it remains a thought experiment. Its purpose is not to establish a conclusion, but to reveal a problem. Many presentations quietly transform the existence of a problem into evidence for a preferred solution. That transformation is philosophically tempting, but logically invalid. The existence of competing interpretations tells us that the foundations of quantum mechanics remain unsettled. It does not tell us which interpretation is correct. The presentation repeatedly treats Wheeler's participatory universe as though it represents the natural destination of quantum theory. Historically, Wheeler's ideas were far more speculative. John Wheeler was one of the greatest physicists of the 20th century. His contributions to nuclear physics, gravitation, and black hole theory are beyond dispute. Yet Wheeler himself was famous for asking radical questions. Many of those questions proved fruitful. Some did not. The participatory anthropic principle belongs to the category of profound speculation rather than established science. Its importance lies less in what it demonstrates than in what it invites us to consider. Could observers play a deeper role in reality than we currently understand? Perhaps. Could consciousness occupy a fundamental place in nature? Possibly. Could information be more basic than matter? Many serious physicists and philosophers have explored exactly that possibility. But possibilities are not conclusions. Questions are not answers. Speculation is not demonstration. The distinction becomes especially important when the argument begins moving toward theology. Once consciousness is elevated to a cosmological principle, the transition appears natural. An observer is required. Human observers arrive late. Therefore, a prior observer must exist. The prior observer must be universal. The universal observer resembles God. The reasoning feels smooth because every step seems to follow from the previous one. Yet the entire chain depends upon the first premise being true. If consciousness is not required for quantum measurements, the chain breaks immediately. If physical interactions alone suffice, then the necessity of a primordial observer disappears. The universe may still have a creator. It may still possess a transcendent ground. It may still point toward mind in other ways. But quantum mechanics no longer supplies the bridge. And that is the crucial point. the deepest questions remain open. The mystery of consciousness remains. The mystery of existence remains. The mystery of why mathematics describes reality remains. The mystery of why there is something rather than nothing remains. Quantum mechanics has illuminated those mysteries. It has not resolved them, nor has it unambiguously transformed them into evidence for a cosmic observer. The observer has returned to the discussion, but the observer has not yet won the argument. The discussion of fine-tuning is where the argument becomes most persuasive to many listeners, and also where the gap between physical observation and philosophical interpretation becomes easiest to overlook. The basic observation is not controversial among physicists. A number of parameters in our best current theories appear to fall within ranges that allow for the existence of complex chemistry, long-lived stars, and structured cosmological evolution. If any of these parameters were significantly different, the universe as we know it would not exist. The strong nuclear force, the masses of fundamental particles, the cosmological constant, and the initial entropy conditions all play roles in determining whether atoms, molecules, and gravitationally bound structures can form. From this, it is tempting to conclude that the universe is in some sense set up for life. And from there, it is a short step, at least rhetorically, to the idea that it was intentionally arranged. But the logical structure of that step depends on assumptions that are not established by the data itself. What physics gives us is a set of conditional facts. If the constants are what they are, then complex structures are possible. If they were different, those structures might not exist. What physics does not directly provide is a probability distribution over possible constants, nor a mechanism that tells us whether the observed values are typical, atypical, necessary, or selected. One of the central issues is that the phrase fine-tuning quietly introduces a comparison class that is not given by experiment. To say a parameter is fine-tuned is to imply that there exists a wider space of possible values, and that only a narrow subset of that space permits complexity. But physics does not currently specify how that space should be measured. Without a well-defined measure, it is difficult to say what counts as likely or unlikely. For example, the cosmological constant is often cited as an extraordinary case because naive calculations from quantum field theory seem to predict a vacuum energy density vastly larger than what is observed. Yet this mismatch, while real, does not automatically imply design. It may indicate that the effective theories we are using are incomplete, or that some cancellation mechanism we do not yet understand is at work, or that our assumptions about how vacuum energy gravitates require revision. Historically, large discrepancies between theory and observation have more often led to new physics than to metaphysical conclusions. The ultraviolet catastrophe did not imply an external fine-tuner. It implied that classical assumptions about energy distribution were wrong. The same caution applies when considering the so-called life-permitting ranges of physical constants. It is often said that small changes in these constants would make life impossible, but this claim depends heavily on what one means by life and how broadly one defines possible forms of structure. Much of the argument assumes carbon-based chemistry and star-driven thermodynamics that's both similar to what we observe, but it is not clear that this is the only conceivable basis for complexity. More importantly, even within the domain of known physics, it is difficult to rigorously demonstrate how sensitive complex structure formation really is to simultaneous variation of multiple parameters. Changing one constant while holding all others fixed may produce dramatic effects, but that does not necessarily reflect the behavior of the system under coordinated variation. In high-dimensional parameter spaces, intuition derived from one-dimensional changes can be misleading. A region that appears finely tuned along one axis may be part of a broader manifold of viable configurations when all degrees of freedom are considered together. Another key assumption in fine-tuning arguments is that the constants of nature are freely variable features of reality, like dials on a control panel. This picture is conceptually useful, but not obviously correct. It may turn out that what we call constants are not contingent values selected from a range of possibilities, but rather derived quantities fixed by deeper principles we have not yet discovered. In such a case, the appearance of fine-tuning would be an artifact of incomplete theoretical understanding. The history of physics provides several examples where quantities once thought arbitrary were later shown to be constrained. What appeared to be independent parameters turned out to be linked by deeper structure. If something similar is true at a more fundamental level, then the space of possible universes may be far smaller than the fine-tuning argument assumes. The multiverse is often introduced at this point as a potential escape from the inference to design. If there are many universes with different values of physical constants, then it is not surprising that at least one of them permits life, and unsurprising that observers find themselves in such a universe. This anthropic reasoning is logically coherent, but it shifts the explanatory burden rather than eliminating it. It explains why we observe life-permitting conditions conditional on our existence, but it does not explain why a multiverse-generating mechanism exists in the first place, nor why it has the properties it does. Moreover, multiverse proposals themselves arise from specific physical theories, such as certain interpretations of inflationary cosmology or string theory landscapes, that already assume a substantial amount of mathematical structure. The multiverse does not remove structure from the explanation, it relocates it. At the same time, it is important not to overstate what multiverse theories do or do not accomplish. In some versions, the multiverse is not an ad hoc addition, but a natural consequence of otherwise well-motivated physical models. Eternal inflation, for example, arises from plausible extrapolations of inflationary dynamics. The string theory landscape emerges from attempts to classify consistent vacuum states in higher dimensional theories. Whether these frameworks correspond to physical reality remains an open question, but they are not arbitrary inventions designed solely to avoid philosophical implications. The scientific status of the multiverse is therefore more nuanced than either enthusiastic endorsement or outright dismissal suggests. It occupies an intermediate position where theoretical motivation exists but empirical access is limited. What fine-tuning arguments ultimately reveal, regardless of one's interpretation, is a tension between explanation and observation that has not yet been resolved. The universe appears in some respects remarkably structured, and in other respects stubbornly resistant to derivation from simpler principles. This combination invites multiple responses. One can interpret the structure as evidence of design, or as evidence of deeper physical necessity, or as evidence of selection effects within a larger ensemble, or as a reflection of limits in our current understanding of probability and cosmology. What cannot be concluded from the data alone is that any single one of these interpretations has been decisively confirmed. The deeper philosophical issue is not whether the universe could have been different, but what it means to say that it could have been different at all. This question reaches into the foundations of physical law. If the laws of physics are necessary, then the constants are not chosen, but derived. If the laws are contingent, then we must explain why this particular set of laws is realized rather than another. If all mathematically consistent laws correspond to physical realities, then the notion of selection becomes anthropically indexed rather than externally imposed. Each of these possibilities carries profound metaphysical implications, but none is currently established by experiment. Fine-tuning, therefore, functions less as a conclusion and more as a pointer toward incompleteness. It highlights the fact that our best theories do not yet explain why they take the form they do. Whether this incompleteness ultimately points toward design, deeper physical principles, or a radically different understanding of explanation itself remains an open question. What is clear is that the inference from fine-tuning to intention is not a straightforward deduction from physics, but a philosophical interpretation layered on top of it. The strength of that interpretation depends not only on the data, but on the broader metaphysical commitments one is willing to adopt in order to make sense of the data. In that sense, fine-tuning does not resolve the question of ultimate explanation. It intensifies it. It forces the question into sharper focus without providing a uniquely determined answer. And that is precisely why it continues to generate debate across physics, philosophy, and theology. The universe, as it presents itself through current scientific understanding, is not silent on the question of meaning or origin, but neither is it univocal. It speaks in multiple possible interpretations at once, and the task of deciding between them lies somewhere beyond the reach of physics alone. The claim that the universe began to exist carries an intuitive force that is difficult to resist, largely because it aligns with everyday experience. In ordinary contexts, things that begin to exist have identifiable causes. Tables are built, organisms are born, fires are ignited, structures are assembled from prior materials. Extending this pattern outward, it feels natural to assume that the universe itself must belong to the same category of things. If everything within the universe begins to exist and has a cause, then it seems reasonable to ask what caused the universe as a whole. This is the intuitive backbone of cosmological arguments that move from a temporal beginning to a transcendent cause. However, when this intuition is applied at the level of cosmology and fundamental physics, it encounters conceptual structures that do not fit neatly into the categories inherited from everyday experience. Modern cosmology does indeed describe a universe that evolves from an early hot, dense state approximately 13.8 billion years ago. This model is supported by multiple independent lines of evidence, including the expansion of space, the cosmic microwave background, and the observed abundances of light elements. What is often less clearly communicated in popular presentations is that this just as early state is not necessarily a boundary of physical existence. It is a boundary of classical description. The equations of general relativity, when extrapolated backward under reasonable assumptions, indicate that spacetime curvature increases without bound, and densities diverge toward a singularity. But in physics, singularities are not typically treated as physical objects or events. They are treated as signs that the theory being used has ceased to be valid in that regime. In other words, the Big Bang singularity is widely interpreted not as a confirmed physical state of infinite density, but as an indication that a more complete theory of quantum gravity is required to describe the earliest phases of the universe. This distinction matters because much of the philosophical weight placed on the beginning of the universe depends on treating the singularity as a literal event in time. If time itself is part of the system described by the theory, then extrapolating the equations to a point where time ceases to be well defined raises questions about whether the notion of before retains its meaning. In some approaches to quantum cosmology, time is not fundamental but emergent, arising from more basic relationships between physical degrees of freedom. In such frameworks, asking what happened before the universe began may be analogous to asking what is north of the North Pole. The structure of the question assumes a framework that may not apply at the deepest level of description. The Borde-Guth-Vilenkin theorem is frequently cited as strengthening the claim that the universe must have had a beginning, but its precise meaning is often overstated in popular accounts. The theorem demonstrates that any spacetime with a positive average expansion rate is past geodesically incomplete, meaning that there are trajectories that cannot be extended indefinitely into the past. This result is significant because it applies broadly across many cosmological models, including inflationary scenarios. However, geodesic incompleteness does not specify what, if anything, lies beyond the boundary of applicability. It does not entail that spacetime emerged from absolute nothingness, nor does it describe a creation event in the metaphysical sense. It indicates that classical spacetime descriptions cannot be extended arbitrarily far backward along certain paths. What replaces or underlies that description remains an open question in theoretical physics. Alternative proposals in quantum cosmology further complicate the idea of an absolute beginning. In some models, such as those inspired by Hartley and Hawking's no-boundary proposal, the early universe is described using a Euclideanized spacetime geometry in which the classical notion of time gradually emerges from a smooth, finite structure without a sharp boundary. In such pictures, the universe does not begin in the traditional sense, but transitions from a regime where temporal ordering is not well defined into one where time becomes a meaningful parameter. Other approaches, including certain bouncing cosmologies, propose that the observable expansion phase may have been preceded by a contracting phase, avoiding a singular beginning altogether. These models are not experimentally confirmed, but they demonstrate that the inference from current cosmological data to an absolute temporal beginning is not the only theoretically available interpretation. The philosophical argument that the universe must have a cause because it began to exist depends crucially on how beginning is defined. If beginning means having a first moment of time, then the argument presupposes that time itself is a linear structure extending infinitely or terminating at a boundary. But if time is emergent, or if cosmological models replace classical singularities with non-singular transitions, then the concept of a first moment becomes less clear. Causation itself, as understood in physics, is typically defined within temporal frameworks. Causes precede effects in time. Yet if time is part of what is being explained, then applying temporal causation to the origin of time requires careful reinterpretation. Some philosophers distinguish between temporal causation and more general notions of dependence or grounding. Even if such a distinction is accepted, moving from physical description to metaphysical conclusion requires additional argumentation that is not supplied by cosmological equations alone. There is also a deeper epistemic issue. Our access to the earliest epochs of the universe is indirect. We infer conditions near the Big Bang from present observations combined with theoretical models. Those models are extremely successful within their tested domains, but they are extrapolated far beyond experimentally confirmed regimes when applied to the Planck era. It is precisely in this regime that quantum gravitational effects are expected to become dominant, yet no complete, empirically verified theory of quantum gravity currently exists. This means that claims about absolute beginnings rest on a mixture of strong empirical support and significant theoretical extrapolation. The boundary between established physics and speculative extension is therefore easy to blur in public discourse. None of this implies that the universe is eternal in the past, nor does it imply that it is not. The point is more modest. The question is not settled by current physics. Both finite and non-finite past models remain actively studied. Some versions of inflationary cosmology, cyclic models, and quantum gravity proposals allow for past eternal structures under certain conditions, while others suggest finite temporal origins. The empirical data do not yet uniquely select among these possibilities. As a result, using cosmology as a decisive argument for a metaphysical first cause requires additional philosophical premises beyond the scientific evidence itself. The deeper issue underlying many of these arguments is the assumption that every chain of explanation must terminate in a first member of a particular kind, often described as necessary, uncaused, or self-existent. This intuition has a long philosophical history and remains influential because it provides a sense of closure. However, modern theoretical frameworks do not always conform to linear chains of dependence. In some cases, explanations are global rather than sequential, arising from constraints on entire structures rather than stepwise causal histories. In other cases, the notion of a foundational first element may be replaced by mutually constraining systems, in which no single element plays the role of an absolute starting point. Whether the universe ultimately requires a terminating explanation of this kind is itself a live philosophical question rather than a settled scientific result. What emerges from contemporary cosmology, therefore, is not a simple confirmation of a temporal beginning that straightforwardly implies a transcendent cause, but a more complex landscape in which the nature of time, causation, and cosmological origin remain partially unresolved. The early universe is well described within certain frameworks, but what lies at the edge of those frameworks is still under active investigation. As with many frontier questions in physics, the most honest conclusion is not that we have reached a definitive answer, but that we have reached the limits of current understanding. The temptation to fill that limit with metaphysical certainty is understandable, but the physics itself taken on its own terms, remains more cautious. It describes a universe with a deeply informative past, a well-supported expansion history, and a mathematically constrained evolution. Whether that history represents an absolute beginning, a boundary of description, or a transition from a deeper structure is still an open question. And it is precisely at that boundary of openness that philosophical interpretation begins to take over from empirical science. If we take quantum mechanics seriously in the way it is actually written, not the simplified versions, not the metaphorical summaries, but the formal structure itself, then one thing becomes immediately clear. The theory never explicitly tells us what counts as an observation, and yet every practical use of the theory depends on exactly that distinction. The Schrödinger equation evolves smoothly, continuously, deterministically, without any special role assigned to measurement, consciousness, or collapse. And yet, whenever we connect the equation to anything we can actually experience in a laboratory, we are forced to introduce a boundary between the quantum description and the classical outcome. That boundary is not derived from the mathematics. It is imposed on top of it. In the Copenhagen tradition, that boundary is simply accepted as fundamental. At some point, systems become classical enough to count as measurements, and the wave function is said to collapse into a single outcome. But the theory itself never specifies where that line is or what physical mechanism enforces it. It works in practice because the rule is operational. If you perform a measurement, you apply the projection rule and update probabilities. But operational success is not the same as ontological explanation. It tells you how to use the theory, not what the theory is saying about reality underneath it. Many worlds removes that boundary entirely. There is no collapse, no special role for measurement, no division between quantum and classical evolution. Instead, everything evolves under the same unitary dynamics, and what we call a measurement outcome is simply the observer becoming entangled with a particular branch of the wave function. From the outside, the mathematics is elegant and self-contained. Nothing is added, nothing is removed. But from the inside of experience, something very specific still seems to happen. A single outcome is perceived, not a superposition of all outcomes. The theory explains this by saying that all outcomes occur, but in different branches that no longer interfere. The difficulty begins when we ask what it means to say, all outcomes occur. Because in order for that statement to carry meaning, we must already assume a notion of identity across branches. We must assume that there is something that counts as me prior to branching, and that this me can be meaningfully related to multiple future versions of itself. Probability then becomes not a question of which outcome will happen, but which version of me I should expect to find myself as. And that is where the Born rule re-enters the story, not as something derived from dynamics alone, but as something that must be imposed as a rule of self-location within the branching structure. Attempts to derive the Born rule within many worlds, through decision theory, rationality constraints, or typicality arguments, are all attempts to recover this missing link without adding new physics. But each attempt quietly introduces assumptions about what counts as rational expectation, or what counts as a typical observer within the wave function. The result is that probability does not disappear in many worlds. It is re-expressed in a more abstract form, where it becomes a statement about how an embedded observer should weight future versions of itself across a structure where everything already exists. Bohmian mechanics approaches the same problem from a completely different angle by insisting that particles always have definite positions, guided by a wave function that never collapses. Here, the observer problem is avoided because there is always a single, actual configuration of matter, even if the wave function itself contains a much richer structure. But this clarity comes at the cost of introducing non-locality in a very strong sense. The guiding wave must encode information about the entire configuration of the universe instantaneously, meaning that the theory cannot be cleanly embedded into a purely local, relativistic space-time picture without additional interpretive machinery. The universe becomes deterministic again, but not in a way that respects the locality we are used to from classical field theory. Objective collapse theories like GRW take yet another route by modifying the Schrödinger equation so that superpositions spontaneously reduce to definite outcomes with a fixed probability per unit time. In this picture, collapse is not an illusion and not an update of knowledge. It is a real physical process. The wave function is not just evolving, it is occasionally being forced into localized states by a mechanism built into the laws of nature. This restores a single outcome without requiring observers or branching, but it does so by introducing new physical parameters that are not derived from deeper theory, but chosen to match experimental constraints. The theory becomes more classical in its outcomes, but more complex in its underlying structure. Across all of these interpretations, a pattern becomes visible. Every attempt to resolve the measurement problem either multiplies unseen structure, modifies fundamental dynamics, or shifts the meaning of probability and reality itself. None of them succeeds in removing the interpretive layer entirely. The mathematics remains unchanged, which means the empirical predictions remain the same. But the question of what the mathematics is actually describing remains open. And because that question remains open, the role of the observer, whether explicit, implicit, or distributed across branches, never fully disappears. When we move from quantum mechanics to cosmology, the scale changes, but the structure of the problem remains strikingly similar. The standard cosmological model is supported by multiple independent lines of evidence that converge on a single narrative. An expanding universe that began in a hot, dense state and has been cooling and evolving for roughly 13.8 billion years. The cosmic microwave background provides a snapshot of an early thermal universe. The abundance of light elements matches predictions from nucleosynthesis in that early phase, and the large-scale distribution of galaxies reflects the growth of small initial fluctuations under gravity. These are not speculative pieces of evidence. They are among the most precisely measured quantities in all of science. Yet, when we extrapolate this model backward, using general relativity, we reach a point where densities and curvatures increase without bound, and the classical description ceases to be valid. The singularity theorems of Penrose and Hawking formalize this by showing that under very general conditions, space-time cannot be extended indefinitely into the past. The Bort-Guth-Vilenkin theorem strengthens this conclusion even for inflationary models, demonstrating that any universe with a positive average expansion rate must be past incomplete. What these results tell us is not the detailed physics of the beginning, but the structural fact that the classical description of spacetime has a boundary. At this boundary, different proposals attempt to continue the story. Eternal inflation suggests that our observable universe is just one region of a larger inflating background that produces many bubble universes. Quantum cosmology proposes wave functions of the universe that describe the emergence of spacetime itself through tunneling or no boundary conditions. Other approaches modify gravity or introduce new pre-geometric structures in which spacetime is not fundamental but emergent. But in every case, the same pattern reappears. The explanatory framework is extended, but never self-grounding. Something is always assumed in order to explain everything else. And this is where the connection back to quantum interpretation becomes unavoidable. In both cases, we are dealing with a theory that is extremely successful at describing conditional structure. Given a framework, it tells us how systems evolve, but that does not determine its own foundational level. Quantum mechanics does not specify why there is a unique outcome without interpretation. Cosmology does not specify why there is a universe with these laws rather than another. In both cases, the formalism is complete as a predictive machine, but incomplete as a self-explanatory system. So the observer problem and the origin problem begin to look like two expressions of the same underlying tension. In quantum mechanics, the tension appears as the question of how definite outcomes arise from a wave function that evolves without collapse. In cosmology, it appears as the question of how a universe arises from a framework that already assumes laws, states, and mathematical structure. In both cases, the explanatory chain does not terminate within the system itself without introducing either additional structure or a foundational principle that sits outside the system. This is why the idea of a participatory universe, or any interpretation that places observers or mind-like structure in a fundamental role, keeps reappearing in different forms across physics and philosophy. It is not because the equations demand it directly, but because the combination of quantum measurement and cosmological origin leaves open a shared structural gap, the transition from mathematical possibility to definite reality. Whether that gap is filled by branching worlds, hidden variables, collapsing dynamics, cosmological multiverses, or observer-centered frameworks, the gap itself does not disappear. Once the observer problem in quantum mechanics and the origin problem in cosmology are placed side by side, something subtle becomes harder to ignore. Every proposed escape from one of these problems tends to reintroduce the other in a different form. The structure of the reasoning does not collapse, but it refuses to stabilize. Each time the theory is adjusted to remove a conceptual tension, the tension reappears one level higher, now embedded in the very framework that was supposed to resolve it. It begins to look less like two separate unsolved problems, and more like a single recurring pattern in how physical explanation behaves when pushed to its limits. In many worlds, the measurement problem is declared non-existent because all outcomes occur. There is no collapse, no special moment where the wave function becomes one thing rather than another, and therefore no need for an observer-triggered transition. But the cost of this resolution is that reality is no longer a single sequence of events. It is a vast branching structure in which every quantum interaction produces a proliferation of non-communicating histories. The theory remains internally consistent, but it replaces selection with coexistence. And once coexistence is taken seriously, the question of probability reappears in a more abstract form. Not why one outcome happens, but why any particular observer should find itself in one branch rather than another, and why the weighting of those branches follows the Born rule at all. In Bohmian mechanics, the strategy is almost the opposite. Instead of multiplying outcomes, it restores a single actual configuration guided by a universal wave function. The observer never splits, because there is always a definite particle arrangement that constitutes the experienced world. But this comes at the price of a deep non-locality that cannot be removed without breaking agreement with quantum predictions. The guiding wave must encode global information instantaneously, meaning that what looks like local evolution in spacetime is underpinned by a structure that is not local in any classical sense. The theory restores definiteness, but it does so by relocating complexity into a hidden layer of global coordination. Objective collapse theories attempt to avoid both branching and hidden variables by modifying the dynamics itself. The wave function does not merely evolve, it occasionally and spontaneously reduces to definite outcomes, according to new physical laws. This restores a single world without requiring observers or hidden configurations, but only by introducing new constants and mechanisms that have not been derived from deeper principles. Collapse becomes a real physical process, but one that is added to the theory, rather than emerging from it. And although such models are, in principle, testable, their deviations from standard quantum mechanics are extremely subtle and remain experimentally constrained rather than confirmed. At this point, the pattern becomes difficult to miss. Every proposed solution to the measurement problem either multiplies unseen structure, modifies the fundamental equations, or reinterprets the meaning of probability and reality itself. None of them eliminates the need for interpretive supplementation. They only change where that supplementation is located. The formalism remains fixed, and the disagreement shifts to what the formalism is allowed to represent. That is why the debate persists, even after decades of technical refinement. It is not a disagreement about calculation, but about ontological interpretation of the same calculation. When the discussion shifts to cosmology, the same structural pattern reappears, but now at the level of the entire universe. The standard cosmological model is not speculative in its core claims. The expansion of space is directly observed through redshift measurements. The cosmic microwave background provides a detailed snapshot of a hot, dense early phase. The abundance of light elements matches the predictions of primordial nucleosynthesis with remarkable precision. Large-scale structure follows naturally from the growth of small initial perturbations under gravity. Taken together, these observations form a tightly interlocking empirical picture that is among the most successful in all of science. But when this picture is extrapolated backward in time using general relativity, it leads to a regime where densities and curvatures increase without bound, and the classical description ceases to function. The singularity theorems of Penrose and Hawking formalize this by showing that under broad and physically reasonable conditions, space-time is geodesically incomplete in the past direction. The Borde-Guth-Vilenkin theorem extends this conclusion to inflationary cosmologies, demonstrating that even eternally inflating models cannot be past eternal if they satisfy a positive average expansion condition. What emerges from these results is not a detailed description of the beginning, but a structural boundary beyond which the classical notion of spacetime cannot be extended. At this boundary, multiple strategies appear. Some propose that the universe is part of a larger multiverse in which our observable region is just one realization among many. Others propose quantum cosmological models in which spacetime emerges from a more fundamental wave function defined over abstract configuration space. Still others suggest modifications to gravity or new pre-geometric frameworks in which spacetime is not fundamental at all. But in each case, the structure of explanation remains the same. The framework is extended, but the extension itself requires new assumptions. The attempt to eliminate a beginning does not remove foundational input. It relocates it into a deeper or more abstract level of description. And here, the parallel with quantum interpretation becomes more than superficial. In both cases, the theory provides a highly successful rule for generating conditional structure. Given certain inputs, it predicts how systems evolve, how correlations form, and how observed quantities distribute. But in neither case does the theory uniquely determine its own foundational interpretation. Quantum mechanics does not specify whether outcomes are selected, branched, guided, or collapsed. Cosmology does not specify whether the universe is unique, part of a multiverse, or emergent from a deeper pre-spacetime structure. The formalism is powerful, but it is not self-interpreting. This is where the idea of explanatory escape becomes relevant. Each interpretation can be seen as an attempt to escape a particular conceptual pressure point. Many worlds escapes collapse. Bohmian mechanics escapes indeterminacy. GRW escapes observer dependence. Inflationary cosmology escapes fine-tuned initial conditions. Quantum creation models escape classical singularities. Multiverse models escape uniqueness. But what they all share is that none of them escapes the need for a framework that is simply taken as given. The escape always works locally, within a specific problem domain, but globally the structure of assumption remains. At a deeper level, this suggests that physics does not eliminate the need for foundational commitments. It distributes them. One can choose to place that foundation in dynamical laws, in initial conditions, in mathematical structures, in ensembles of universes, or in interpretive rules about observation and probability. Each choice produces a different metaphysical picture, but none of them removes the requirement that something must be treated as basic in order for explanation to proceed at all. The disagreement is not over whether there is a foundation, but over what kind of thing is allowed to play that role. And so, both quantum mechanics and cosmology converge on a shared structural limit. The limit is not experimental, it is conceptual. It appears whenever a theory is asked not just to predict outcomes within a framework, but to account for why that framework exists and why it takes the form it does. At that point, the theory can continue to expand, but it cannot close on itself without introducing either new layers of structure or terminating principles that are not derived in the same way as everything else. If you continue the thread far enough, past interpretation and argument, past the competing models of collapse and branching, and hidden variables and observer relative facts, you eventually arrive at a place where physics stops feeling like a set of answers and starts behaving like a description of limits. Not limits in the sense of what we can measure, but limits in the sense of what it even means for something to be definite at all. Quantum theory, in its most careful formulation, does not really describe objects sitting in space with properties attached to them. It describes a structure of possibilities evolving smoothly, without interruption, without preference, until something in the framework forces a single outcome to be registered. The mystery is not that outcomes are uncertain. The mystery is that outcomes are ever definite in the first place. In the laboratory, this feels contained. A detector clicks, a screen lights up, a particle appears here and not there. The language of measurement hides the deeper strangeness because it suggests a simple interaction between a system and a device. But when you strip that language away, what remains is a physical process that, according to the equations, should not single anything out. The equations only spread amplitudes. They only extend superpositions. They never, on their own, choose. And yet the world we experience is made entirely of choices already made. Not potential realities, but settled ones. Not superpositions, but records. So the question that keeps returning, no matter how many interpretations are layered over it, is not what the wave function does, but what it means for anything to become an event. Because an event is not just a mathematical point in a Hilbert space. An event is something that is true in a way that excludes its alternatives. And exclusion is the real puzzle. Physics describes how amplitudes interfere, how probabilities distribute, how correlations form across distance and time. But nowhere inside the formalism is there a place where alternatives are eliminated. They simply stop being relevant in practice. The world behaves as if one branch has been selected, but the theory itself never performs the selection. This is why every interpretation, in its own way, becomes an attempt to relocate the moment of selection. Many worlds moves it outward, dissolving it entirely into a branching structure where nothing is ever lost, only separated. Collapse theories move it inward, embedding it into the dynamics as an actual physical process that occurs spontaneously or gravitationally. Hidden variable theories move it beneath the surface, insisting that nothing ever becomes indeterminate in the first place, only unknown. Epistemic theories move it into the mind, where the act of updating belief replaces the need for physical selection. And relational approaches dissolve the idea of global selection altogether, replacing it with a network of local facts that never need to agree from a single universal perspective. But what all of these approaches share, beneath their differences, is the acknowledgement that standard quantum evolution alone is not enough to account for the definiteness of experience. Something extra is always being added, or removed, or reinterpreted. The formalism is stable, but the meaning is not. If you slow down the picture further, if you imagine the universe not as a collection of experiments, but as a single continuous quantum system evolving from its earliest state, the same tension appears at a larger scale. The early universe, according to our best cosmological models, begins in an extremely low entropy configuration, a state so special that almost every possible configuration would not resemble it. From that fragile beginning, structure emerges. Particles form, atoms bind, stars ignite, galaxies cluster, and eventually observers appear who can ask what any of it means. But at no point in this unfolding does the underlying equation specify where the boundary between possibility and actuality lies. It is tempting to say that decoherence solves this, that interaction with the environment suppresses interference and produces classical outcomes. And in a practical sense, it does. It explains why macroscopic superpositions are not observed. But decoherence, on its own, does not select a single outcome. It distributes amplitude across effectively non-communicating branches. It replaces interference with isolation, not with uniqueness. The world becomes a collection of parallel classical-like histories that do not interact. But the question of why one of them is experienced as this one remains untouched. This is where the notion of an observer becomes unavoidable again, not as a conscious agent watching the universe from outside, but as a structural feature of how definiteness is represented. An observer, in the most minimal sense, is anything that registers a record that persists, a memory, a trace, a correlation embedded in physical degrees of freedom. But even when defined this way, observers do not solve the problem of selection. They only mark where selection appears to have already occurred. They are downstream of definiteness, not its source. And yet, from the inside of the universe, there is no access to anything other than these records. Every experience is already a record. Every measurement is already a memory. Every moment is already a collapsed history from the perspective of the system that contains it. The universe, as it is accessed, is always post-selection. This creates a kind of asymmetry that is easy to overlook. The equations describe a full space of possibilities, but experience navigates only a single realized strand. There is no viewpoint from which the full structure is visible at once. Even attempts to reconstruct it are themselves part of one branch. So the quiet edge of reality is not a boundary in space or time. It is the boundary between what is contained in the formal description and what is encountered as fact. Physics, at its deepest level, seems to oscillate between these two descriptions without ever fully reconciling them. The formalism remains open, but the world is closed. The wave function remains extended, but experience is punctual. And the tension between these two is not resolved by adding more structure within the same framework. It persists as long as the framework remains purely dynamical. If you follow that tension without trying to resolve it prematurely, it begins to feel less like a technical problem and more like a statement about perspective. The universe described from the outside is a superposition. The universe lived from the inside is a sequence of definiteness. These are not two different universes, but two incompatible ways of representing the same one. The interpretational burden arises from trying to collapse these perspectives into a single picture without remainder. At the deepest level, what quantum theory may be telling us is not simply that reality is strange, but that reality itself is not a single kind of thing. There is the evolving structure of possibilities, and there is the lived sequence of outcomes. One is complete without selection. The other is complete only through selection. The bridge between them is what every interpretation tries and fails to fully stabilize. And so the quiet edge remains, not as a failure of physics, but as the place where physics ends and description begins to point back at itself. At some point in every attempt to describe reality completely, there is a subtle shift that happens without announcement. The language stops pointing outward and begins to curve back toward the act of description itself. It is not that the universe changes, but that the framework being used to talk about it becomes visible as a framework. Quantum theory is especially prone to this effect because it does not merely describe objects in the world. It describes the conditions under which objects in the world becomes a meaningful phrase at all. And when a theory begins to include the observer, the measurement, the information, the record, it slowly starts to resemble not just a map of reality, but a map of how mapping is possible. In classical physics, the world appears as something complete and self-contained. There are particles, fields, forces, trajectories. Even if we do not know everything about them, the assumption is that everything has a definite state, regardless of whether it is known. Quantum theory removes that comfort without fully replacing it with anything equally intuitive. Instead, it replaces definiteness with structure, and structure with evolution, and evolution with a rule that never quite produces a single outcome on its own. What we call reality then becomes something that emerges at the level of interaction, not something that exists in finished form at the base level of the equations. This is why the act of observation cannot be easily treated as just another physical process among others. It is not special because of consciousness or complexity, but because it marks the transition point where a range of possibilities becomes a single, recorded history. A detector click is not just an event in space. It is the end of a superposition from the perspective of everything that will later treat that click as a fact. And yet the equations that govern the detector do not contain any internal instruction that says, this is the moment where alternatives stop being alternatives. They only describe continuous evolution. When this is extended across the entire universe, the tension becomes more abstract, but also more total. There is no external laboratory, no outside experimenter, no higher vantage point from which the universe is being measured. And yet, Within the universe, there are always subsystems that behave as if outcomes are definite. Records exist, memories accumulate, stars explode in one way rather than many, histories appear fixed. The question is not whether these things happen, but how the formalism accounts for the appearance of a single realized history when the underlying description contains many. Different interpretations answer this in different ways, but none of them remove the underlying duality. Either all outcomes exist but are separated, or only one exists but is selected by a process not fully described, or all outcomes are real relative to different contexts, or outcomes are not physical at all but expressions of knowledge. Each option preserves the mathematics, but each one changes what is meant by existence itself. And so the disagreement is not just about physics, but about what kind of thing physics is ultimately describing. If there is a unifying thread beneath all of this, it is the recognition that the universe is not given to us in a raw form. It is always accessed through a structure of interaction. Light must scatter. Systems must correlate. Information must be stored in physical substrates that persist long enough to matter. Even the most abstract cosmological models are ultimately interpreted through data that arrives in detectors, in telescopes, and memories. There is no version of physics that floats entirely free of this constraint, because the act of doing physics is itself part of the physical universe it describes. This leads to a subtle inversion. Instead of asking how observers emerge inside a finished universe, one can also notice that a finished universe is itself a concept that arises inside the activity of observation. The equations evolve independently of us, but what they describe as possibilities becomes the world, only when some subset of those possibilities becomes stable enough to be treated as actual from within the system. In that sense, actuality is not a global feature stamped on reality from the outside. It is something that appears locally, wherever information becomes irreversible. Irreversibility is important here, because without it, every event could in principle be undone, every record erased, every trace unmade. But the universe we experience is not reversible in that way. Entropy increases, information disperses, correlations spread into environments that are too large to reconstruct. And it is this spreading that gives the impression of a single direction of time and a single sequence of outcomes. The arrow of time is not just a feature of thermodynamics. It is the condition that allows experience itself to have continuity. So when we ask where the description ends, it is not a question about a boundary in space or time. It is a question about whether there is a point in the formalism where possibility becomes fact, or whether fact is something that only ever exists relative to a subsystem that cannot access the full structure of possibilities at once. Quantum theory, in all its interpretations, seems to resist giving a final answer to this in a way that feels complete from every angle. It either multiplies worlds, multiplies rules, multiplies perspectives, or multiplies the meaning of knowledge itself. And yet, despite this unresolved structure, the universe does not feel incomplete from the inside. It presents itself as continuous, stable, and singular. The night sky does not appear as a branching tree of possibilities. It appears as a single sky. The past does not appear as a superposition of histories. It appears as something fixed. Whatever the underlying description may be doing, the lived structure of reality is one of coherence. This is perhaps the quietest point hidden inside all of modern physics. That a complete description of reality may not look like a single, unified story told from nowhere. It may only ever exist as a relationship between a mathematical evolution and a perspective embedded inside it. The universe, as described, and the universe, as experienced, are not competing versions of reality. They are two layers of the same process, neither of which fully contains the other on its own. So the attempt to locate a final observer, or a final cause, or a final selection mechanism may be missing the deeper structure entirely. It may be that there is no final point in the chain where everything becomes simple and closed. Instead, there is only a continuous unfolding in which structure generates structure. And within that structure, localized regions arise where the unfolding is experienced as a sequence of definite moments. From this point of view, the question, who observes the universe, gradually transforms. It stops pointing toward a single entity and starts pointing toward a relationship. The relationship between a system that evolves according to amplitudes and a subsystem that registers outcomes as facts. The mystery is not eliminated, but it becomes less like a missing piece and more like a persistent feature of how description itself is constructed. And when the mind follows that thought all the way down, it reaches a kind of stillness. Not because everything has been explained, but because the expectation of a single place where everything locks into place begins to dissolve. The universe does not need to close in order to be coherent. It only needs to remain consistent in how possibilities relate to experiences. In the end, what remains is not a final answer, but a stable recognition of how limited any single perspective must be inside a system that contains all perspectives. Physics continues, observation continues, description continues, and reality, whatever it ultimately is, does not wait for it to finish. So as this sequence of ideas fades, there is nothing left to solve in this moment, only the quiet continuation of everything still unfolding in its own way, according to its own structure, long after any one description has reached its edge. If you are listening to this as you drift toward sleep, you can let the questions remain unanswered for now. They do not need to be completed to be held gently in the mind. The universe does not pause for understanding, and you do not need to follow it any further tonight. This is space sleep theory, and this is where the description rests.